The tangential speed on the outer edge of a rotating carousel is... Okay, that's the question. Take a look at this carousel with a ladybug sitting on the outer edge. You see two vectors, a green velocity vector and a red acceleration vector. Let me speed things up so you can see these arrows a little more clearly. And technically, they're not arrows, they're vectors. So here, again, this green vector is the tangential velocity vector. Tangent means at a right angle to the arc radius, or the circle radius, as you see here. This red vector is the centripetal acceleration vector. It's always changing direction, but it's always pointing towards the center of rotation. If things really speed up, notice how these vectors are getting longer. The tangential velocity is increasing, and the centripetal acceleration, which is again the red vector, is also getting bigger. If I slow things down, the tangential velocity vector, the green vector, is much smaller, and so is the red centripetal acceleration vector. This ladybug is never moving toward or away from the center. So in terms of its velocity towards or away from the center, there is none. The velocity of this ladybug is always in the direction indicated by this green arrow, which one more time we call the tangential velocity vector. Here's another question. The rotational speed of every point of a rotating rigid object is... Okay, let's go back to the ladybug on a carousel. This question is not asking about tangential velocity, it's asking about rotational speed, also known as rotational velocity. Watch what happens when I adjust the rotational velocity of this carousel. I'm going to make it fast, and then I'm going to slow it down and reverse it. Check out the units for rotational velocity, again also known as rotational speed. Right here, for example, it's a 96.83 degrees per second. Everything on this carousel, no matter where it's located, is moving at that same 96.83 degrees per second. Watch what happens if I change the position of the ladybug. Let me pause the animation, move the ladybug to a different position, and you can see the ladybug is still rotating with that same angular velocity, 96.83 meters per second. Also, take a look at the green tangential velocity vector. Look how short this vector gets if the ladybug is moved to the center or near the center of the carousel. Look how short that tangential velocity vector is. However short it is, the rotational speed of the ladybug still remains, however, at 96.83 degrees per second. Now watch what happens when I take the ladybug and I move it out to an edge. The green tangential velocity vector is much longer. It's moving much faster from a tangential velocity point of view, but the rotational velocity of this ladybug remains at 96.83 degrees per second. So this is a good comparison of tangential velocity, which is that green vector, and the rotational speed of the ladybug, which is the same as the rotational speed of every other point on that carousel, because they move in unison. Okay, tangential speed is the linear velocity a rotating object would have at the moment it's released from its circular motion. So imagine you tie a rock to a string and you're swinging that rock over your head in a circle, and then somebody walks up and cuts the string. The rock flies off in a straight line, and that straight line velocity that rock has at that moment is the tangential velocity, which is just a regular old linear velocity. So tangential speed is just a linear speed, but it's kind of special in that it's tangential, meaning it's always making a 90-degree angle to the arc or circular radius. We've had a couple of expressions for linear speed. Velocity is distance over time, or if there's an acceleration, we use final velocity equals initial velocity plus acceleration times time. Here, though, we are just looking at the situation where something is rotating in a circle at a constant speed. So this is why we can use velocity equals distance over time, where distance is the path along the circle or the path along the arc. Let's take a look at rotational speed. Look at this red ball, yellow ball, and green ball. All three are moving in circles. You can see the linear speed of the green ball is greater than the yellow ball, which is greater than the red ball. So if all three balls were immediately released from their path, the green ball would fly off at a greater velocity compared to the yellow ball, and the yellow ball would fly off at a velocity greater than the red ball. So we say the tangential velocity of the green ball is greater than the tangential velocity of the yellow ball, which is greater than the tangential velocity of the red ball. However, all three balls have the same rotational velocity. Let's say for the sake of conversation, the red ball is completing 5 revolutions in 1 minute. That would be the exact same number for the yellow ball and green ball. All 3 balls are completing 5 revolutions in 1 minute, again, for example. So in terms of rotational velocity, also known as rotational speed, we would measure the speed in terms of revolutions per some time unit. In my example, 5 revolutions per minute. Next question, which varies with radial distance on a rotating turntable? Tangential speed or rotational speed? I pretty much covered it, but let me say a few more things just to reinforce. Here's the ladybug at a short radial distance from the center of this rotating turntable. This turntable is not going to speed up or slow down in terms of its angular or rotational velocity. Watch what happens when I increase the ladybug's radial distance from the center of the turntable. That green tangential velocity vector is increasing, but as far as the rotational velocity, the ladybug is rotating at the same rate. It's not speeding up or slowing down in terms of its revolutions per minute. Its revolutions per minute is remaining constant. If I increase the ladybug's radial distance even more, you can see the tangential velocity continues to increase, so that depends on radial location or radius. But in terms of RPMs or revolutions per minute, which is one way to measure angular velocity, or again, that term can be substituted with angular speed or rotational velocity. They all mean the same thing. The rotational velocity remains unchanged. A tapered cup rolled on a flat surface makes a circular path. Does this mean the tangential speed of the wide end rim differs from that of the narrow end rim? Here's what that looks like. This yellow cup is rolling on the floor. It's moving in a circle, so the tangential speed of a point at the wide end of this cup needs to be greater just to keep up. The angular velocity of the narrow end and the wide end are the same. They're both moving in the same circle, so if the rotational speed of the narrow end is, say for example, 2 revolutions per minute, the rotational speed of the wide end of the cup also has to be 2 revolutions per minute. To maintain this 2 revolutions per minute, a point on the wide end of the rim needs to have a greater tangential velocity just to keep up. Last question, how does the tapered rim of a wheel on a railroad train rolling along a track allow part of the rim to roll faster than the other part? For this question, I'm just going to refer you to the textbook. Go on to Mastering Physics and get into the e-textbook for our class, and then go to Chapter 8, Section 1, Circular Motion. This is the one section of Chapter 8 that we're including now. We'll cover the other sections later, but right now, read through Chapter 8, Section 1. There's good reading, good visuals. Here's a YouTube video, and actually there's another whole section within this section covering wheels on railroad trains. So this should very thoroughly cover this question.